start the recording and share my screen. Okay. You remember that during the past lecture, is everything okay? Are you hearing me? Are you seeing the screen? Please answer. Thank you.
Yes, Professor.
Perfect. Okay, so everything is okay. So you remember that basically during the past lecture we have introduced several important concepts concerning the dynamic response, the dynamic and seismic response of structure. First of all, we have understood that for a linear system, for a structure in the linear range of behavior, if we move the structure from its equilibrium position, a sinusoidal motion begins, and of course this sinusoidal motion is characterized by, for example, the distance between two consecutive maximum point, or by the wave length of this sinusoidal wave. If we refer, for example, to the wavelength, the time interval needed for covering an entire wavelength is the so-called natural period. Okay? The natural period, of course, should be also defined in a different way, because, for example, if we are referring not to the natural period, but to the inverse of the natural period, so not t, but 1 over t, we can define the so-called natural frequency. But if we multiply the natural frequency by 2 times Greek p, we can obtain another type of frequency, which is called the circular frequency. But the natural frequency, or the fundamental period, or the circular frequency, we have seen are depending directly on the mass, which means on the weight of the structure, but also on the stiffness of the structure. And we have discussed, basically, I will do again now, the dependence between natural frequencies and on one side, and mass and stiffness on the other side. We can discuss, for example, through this simple website. In addition, we have also discovered that in the linear range, also the dissipation of energy is important for linear structure, because generally for a real structure there is always dissipation of energy. So when we move our structure from its equilibrium position, the response is oscillatory like this, but it is not an indefinitely long sinusoid. It is a damped sinusoid, okay? In addition, we have also discovered another aspect, that every structure is characterized by its mass and its stiffness. And this is the first important comment. But if we have several buildings in the same site, and so those buildings are characterized by different masses, different stiffness, and so different natural frequencies or fundamental period, we have a situation which is very similar to the one illustrated in this movie, and so the same mass which is connected by different springs by springs of different stiffness to the ground. And so what's happening is then when the natural frequency of the oscillation induced to the ground is increasing and it reaches the natural frequency on one of these single degrees of freedom system, what happens is that we have that the response and also the force increases a lot. So basically we have discussed in some detail this aspect on past lecture, and I would like to briefly recall this before beginning the lecture of today. So, first of all, let us refer, for example, to a system like this with no damping, a certain value of the spring constant, and a certain value of the mass. Okay, as we have said, when we move this system from the equilibrium position, you see an up and down motion begins. This up and down motion is a sinusoidal wave, okay? And so the time needed for reaching 2 consecutive maxima, or the time period needed to have an entire wavelength, is the so-called fundamental period. If we refer to the inverse of the fundamental period, basically we can refer to the so-called natural frequency. Okay, if we refer, for example, to natural frequency, what we expect for natural frequencies when the stiffness changes or the mass changes. Okay, if we are referring to the natural frequencies, for natural frequencies, this quantity is proportional to the spring constant. Proportional means that if I increase the value of the spring constant, the natural frequencies increases. Okay, if I decrease the value of the natural of the spring constant, the natural frequencies decreases as well. In addition, if we refer to the effect of the mass, basically, if we increase the mass, the natural frequency decreases. If we decrease the masses, of course, the natural frequencies increases. If we are dealing with the inverse of natural frequencies, that is the fundamental period, of course, the effect of mass and spring changing are basically the opposite. This means, in terms of stiffness, if I increase the stiffness, the fundamental period decreases. On the other side, if I increase the mass, the fundamental period increases. Okay, so let's verify this. For example, first in terms of spring constant. Okay, we have seen that if the mass is not changed and we move the system far from the equilibrium position, we have a certain fundamental period. Okay, if I increase a lot the spring constant, you can see that now the motion has changed and the fundamental period now is lower than before. Okay, now we have a certain fundamental period. Now I will decrease the value of the spring, and so we can observe that the fundamental period now is longer than before. Okay, now let's look, for example, at this value of the spring constant, and we have a certain fundamental period. Okay, now I will change the mass and add a larger mass. So what I expect is that now the motion is slower. So the fundamental period increases by increasing the value of the mass. And if we add damping, basically, we can see that very quickly, in terms of the increase of damping, we have that the motion stop. Okay. We have also seen that beyond this aspect, when we have an experience like this, in which we have several degrees of freedom systems which are mounted on the ground, and the motion of the ground is sinusoidal, and the natural frequency of this ground motion is increasing. What we will observe, for example, for the more deformable of these degrees of freedom system, what we will observe that at a certain point we will see that this single degrees of freedom system begins to accelerate, and X motion becomes very large. Of course, it becomes maximum when the natural frequency of the ground motion becomes exactly equal to the natural frequency of the single degrees of freedom system of our building. So, in fact, now you are seeing that this motion is increasing a lot. And so we have reached the natural frequency of 4 Hertz, and we have that this system is at resonance, okay, with the great amplification of the motion. When the frequency of the motion applied to the ground is increasing, we can see that this motion is decreasing while the motion of another building is increasing, okay? And so, for example, we have the resonance, or we are very close to the resonance of this second building, or this second single degrees of freedom system. So now we have the resonance of the second building corresponding to a natural frequency of 6.35 Hertz. Okay. If we continue, you remember from past lecture, of course, that there will be basically the resonance of the stiffer system. Now, let's go back to our slide and to the content of our lecture. Of course, my idea is to analyze very quickly, basically, the equation describing this kind of mechanical phenomenon. We can basically refer for the basic behavior of a real structure, of a real building, for example, to a single degrees of freedom system. And from dynamic standpoint, we can imagine that a single degrees of freedom system is a mass which is connected to the ground by a spring, by a column, by some stiffness, and also by some dashpot. The dashpot is responsible for the dissipation of energy. Okay, so in the practice, when this single degrees of freedom system is subjected, for example, to an external force which is depending on time, and the external force, for example, is denoted as P. We have an acceleration, a velocity, and one displacement of the system. The acceleration generates, as we have already discussed, an inertia force. The inertia force is proportional to the mass. In addition, we have an elastic restoring force, because when we move the single degrees of freedom system, which is connected to the ground by a spring, when we move this from its equilibrium position, there is a force arising in the spring. And of course, this force in the spring, which is equal to the stiffness of the spring times the displacement, is tending to bring back our single degrees of freedom system to its equilibrium position. There is also a dissipation action, a dissipation force, which is proportional to the velocity, and also this dissipation force is tending to bringing back the system to our original equilibrium. Also, the inertia forces is directed against the acceleration, okay? And so we have this kind of forces, okay? Of course, if we are dealing to a simple building, we can observe that this simple building behaves as a single degrees of freedom system, because we have the mass which is concentrated in this rigid block, and then we have that this rigid block is connected to the ground through flexible columns, and so we have something like this. So this is the ground, possibly subject to a certain motion. Here is the mass of the building, which is basically concentrated at the level of the rigid floor, and here there is the stiffness K of the flexible columns. But of course, we can also imagine some different type of single degrees of freedom system, like, for example, an offshore platform, which is generally a stiff mass which is connected to the ground, in this case to a flexible structure, or to the body of a rigid car, and the body is a stiff element that is connected to the ground through the flexible suspension. And so we have that the flexible suspension acts like some deformable springs. Okay, if first of all we neglect the presence of dissipating action, when we have a single degrees of freedom system under the action of a certain force F, and the force F is depending on time, at each time instant there will be equilibrium between this external force, the inertia force, which is the mass, times the acceleration x2 dot, and of course the elastic restoring force, which is K, the stiffness of the spring, times the displacement x. Okay, now first of all, let's imagine that the external force is equal to 0. So we have exactly a free vibration. So basically, we move our single degrees of freedom system from its equilibrium position, and so we expect that the solution of this problem is a sinusoidal motion. It is very easy to obtain this. In fact, we can very easily verify that the solution of this equation is x equal to capital A exponential of RT. In fact, the second derivative of exponential of RT is R squared exponential of RT. And so we obtain this kind of characteristic equation. If we substitute this one inside this equation, we obtain mr squared plus k equals 0. The solution of this characteristic equation is a solution in imaginary terms. I is the imaginary terms. So plus or minus I times the square root of k over m. If we use the Euler formula, we can state that the solution in terms of displacement is A times cosine omega nt plus B sin omega nt, and omega is the ratio between the square root, omega n is the circular frequency, and it is equal to the square root of the ratio between the stiffness and the mass. Okay? From this value of circular frequency, we can obtain the natural frequency. It's simply equal to omega n over 2 Greek p. Okay? And from this, we can obtain the fundamental period. So we can observe that fundamental period or natural frequency or circular frequency are clearly depending on the stiffness and on the mass. And as we have already stated, if we refer to the frequency, natural either circular frequency, if we increase the stiffness, the natural or circular frequency increases. If we increase the mass, the natural of circular frequency decreases. Okay? So we can very easily obtain the solution of this equation. And we verify analytically what we have already seen by simply examining the typical solution of this kind of mechanical phenomenon, the free vibration of a mass which is moved from its static equilibrium position. Of course, this is very important. The characteristics of the motion are defined in terms of natural frequency, Fn, which is equal to the circular frequency over 2 times Greek p, which is proportional to the square root of the ratio k over m. We can define, of course, the circular frequency as the square root of the ratio of k over m, and we can also define the fundamental period as the inverse value of the natural frequency. So once we have understood how stiffness and mass affects the value of fundamental frequency or natural period, we can clearly know which are the expected dynamic characteristics of our single degrees of freedom system, since we are neglecting the dissipation of energy. Basically we have to expect a sinusoidal motion. Okay, so now let us continue to think that the dissipation of energy is not considered. But now let's apply a sinusoidal motion with an applied circular frequency of omega. We have seen from the results of our movie that what we expect is that when the frequency omega of the forcing function reach the natural or resonant frequency of the single degrees of freedom system, we have a great increase of the response. This might be very easily evaluated, because if we apply a force which is denoted as capital F times exponential of I omega t, we can observe that very easily that the solution of this is in terms of capital X times the same exponential. Now let us to substitute this F and this X in this equilibrium equation. And we observe by doing this that we have K minus omega square m times X times exponential of I omega t equal to capital F times I omega t. Of course, in both sides of this equation, I can simplify the exponential. And then I can obtain that the amplitude of my motion is the amplitude of the applied force over the difference between the stiffness of our system minus omega square, which is the frequency of the applied force, times the mass of the system. Okay? Of course, instead of using this notation of the input force F time exponential of I omega t, sorry again, I can use this kind of notation. I apply a force which is a sinusoidal force like this, sinusoidal force sin of omega t. It's exactly what we have seen in the movie. The ground motion was sinusoidal, and the frequency of this sinusoidal force was increasing in time. Okay, so if we have an applied force like this, we expect that the response is sinusoidal response as well. And so when we substitute, we can obtain minus m omega square plus k times capital X sin omega t equal to the applied force capital F times sin omega t. Of course, we can simplify sin omega t in both members, and we can obtain that the amplitude of the resulting motion is the ratio between the amplitude of the applied force over k minus omega square m. And so this equation says to us that the response to a sinusoidal force of our system, first of all, as expected, depends on the amplitude of the force, for sure. Similarly, and we expect this, it depends on the dynamic characteristic of the system, because it depends on K and it depends on M. So it depends on the stiffness of the system and also on the mass of the system, but it also depends on the natural frequency of the applied motion. So the frequency content of the earthquake is an important parameter. If we observe that the ratio between F and K, that is the value of X for omega equals 0, is the static displacement, okay? So it's what we expect when we applied statically to our spring a force F. The spring has a displacement whose value is equal to F over K. So if we denote the static displacement as x0, we can observe that this value might be expressed as x over x0. So the actual value of the displacement corresponding to the value of omega. Okay, this is x over x0, and it is equal to 1 over 1 minus omega square over omega square n. And so we observe in particular that when omega is equal to omega n, the denominator will be equal to 0. So we have an indefinite amplitude of the motion. There is a large amplification of the motion. So this is exactly what we have seen, that when the frequency of the forcing function becomes equal to the frequency of resonance omega n, we have a great amplification. When omega, so the frequency of the forcing function, is less than the resonant frequency, we have that this value is positive. Otherwise, we have that this value is negative. And so we have a typical curve like this. Okay? So when the frequency of the forcing function increase and approach the resonance, we can observe an increasing of the motion. So there is a large amplification. Otherwise, when we move over the resonance, the dynamic amplification factor becomes to decrease. So this is exactly what we have observed in our movie. And of course, we can obtain this kind of behavior directly from equations in a very easy way. Of course, we can also introduce the action of the damping, and we will do this very quickly. But in addition, for example, it is interesting for us to predict the value of the fundamental period of a building, for example. If we refer to real building, for a real building exhibiting an height lower than 40 meters with a mass distribution which is approximately uniform, we can say that the fundamental period is the product of a constant c depending on the structure, on the type of structure, times h elevated to 3 over 4, okay? The coefficient c is equal to 0.085 for steel frame buildings, is equal to 0.075 for reinforced concrete frame buildings. It's equal to 0.05 for other buildings. For historic masonry tower, we can say that the fundamental period is 0.0187h. Okay, so it's obvious that the dependence on h in some sense introduce the dependence on mass and stiffness of the system. And of course, the value of c basically accounts for also for the stiffness of the structure. Of course, this kind of fundamental period are given directly by our standard code. For example, this value are contained in the Italian NTC emitted in 2018. As I said before, of course, I can easily introduce the damping. The damping in the equation of motion is introduced through a term which is proportional to the velocity. Okay, so if firstly we refer to a free damped oscillation, so no external forces, generally it is better in this case to divide both sides of the equation by the mass of the system. If we are doing this, we can introduce a coefficient xi, which is called damping coefficient. And the damping coefficient is b over 2 times the square root of k times m. By doing this, the equation of motion has this form. Now, if we say that the applied force is equal to 0, we have the equation of the free damped motion. The general solution is exactly as before, capital A time exponential of RT. And so we can write the characteristic equation by derivating 1 times and 2 times x and then obtaining a characteristic equation. In this case, we obtain that the free damped motion might be oscillatory or not, depending on the fact that the damping factor is lower than 1, that is equal to 1, or it is larger than 1. Generally, we are in the case of civil engineering structure, we are in the case in which the damping coefficient is much lower than 1. And so we have an oscillatory motion like this. This is the dynamic behavior of a civil structure, and it's called underdamped. When we have that damping is exactly equal to 1, we have the maximum motion at the beginning, and afterward there is no oscillation. Afterwards, we have an underdamped system without basically any kind of oscillation. But in the field of engineering structure, we have that the general solution is a free damped motion, okay? And the free damped motion is something like this, what is illustrated in this slide, okay? So in the case of zero damping, we have that the amplitude of the motion never decreases, and we have observed in our example in the internet. If we begin to increase the value of the damping coefficient, basically we begin to see that there is a dissipation of energy, and so the motion, the amplitude of the motion, begins to decrease in time. Of course, it decreases much more quickly if we increase the value of the damping coefficient. But generally, when I talk to the students of this kind of phenomenon, I have always the idea that you don't think that equation represent the real behavior. Indeed, this kind of equation, even if they are very simple, represents the real behavior of a building. And in fact, for example, from my experience of working on real structure, I can show an example of this. You can see that this building is a real building, is an historic tower in the town of Mantua. It is 554-meter high. Basically, it is the higher monuments in Mantua, the higher building in Mantua. And you can see that, for example, there was a visual inspection of this element, of this structure, by using an aerial platform. During this inspection, the platform, due to a mistake, hits against the tower, okay? A small hit. So in this case, we have a typical free damped oscillation. During the free damped oscillation, the structure was instrumented by different accelerometers placed at different heights of the tower. An accelerometer is a sensor measuring the response in terms of acceleration. And you can see, for example, that the response in terms of acceleration at a certain point is something like this. So first of all, we can observe that there is no a real quiet of the structure, never. But when you hit the structure, you can observe something that resembles very closely a free damped oscillation. And if we superimpose the structural response at different level of the tower, red, yellow, and green, we can observe that here the real oscillation, the oscillation measured on a real building, is a free damped sinusoid. So is a sinusoidal wave whose amplitude is decreasing in time, and it is decreasing by an exponential curve of something that is very similar to an exponential curve. Of course, we can apply also in the case of a real damping an applied force. And for example, we can apply a sinusoidal force. We can expect a behavior similar to the previous one, with the amplification factor that increases as the frequency of the external force approaches the resonant frequency. But in this case, there is also an effect of the damping. So the amplitude of this peak that was equal to infinite in the previous case when we have no damping becomes lower and lower when we are going to increase the dissipation of energy. Okay, this introduction in order to have the possibility of writing and beginning to discuss the equation of motion of a damped building under earthquake. Because generally, when we are dealing with a real structure and we approximate the real structure as a single degrees of freedom system, as a building, for example, we can approximate a building like a single degrees of freedom system. Generally, we have to remember, first of all, that the inertia forces are proportional to the acceleration. Which kind of acceleration? The absolute acceleration. When there is no ground motion, the acceleration of the mass is exactly equal to the absolute acceleration. But when we have also a ground motion with the ground acceleration x2 dot 0, the absolute acceleration is the summation of the acceleration relative to the ground, x2 dot, plus the acceleration of the ground. Instead, the force of the spring is proportional to the relative displacement, so to the displacement relative to the ground. Similarly, sorry, when we are dealing with the damping force is proportional to the velocity relative to the ground. So if we denote that the displacement relative to the ground is the difference between the absolute displacement and the displacement x0 relative to the ground, so we will have the inertia force, and the inertia force is equal to the mass times the relative acceleration plus the acceleration on the ground. And I put the acceleration of the ground on the right hand side. In addition, on the left hand side, I have to sum up the value of the damping force and the value of the elastic restoring force. So in the case of an earthquake, the external force, the excitation, basically, is the product of the mass times the acceleration of the ground. Of course, it is very important also to know which are typical value of the damping in structure. And for example, in welded steel frame, we can observe that the damping is very low, in the range between 1 or 2%. In uncracked or cracked reinforced concrete, coming to damaged steel structure or damaged concrete structure, we can see that the damping coefficient is generally increasing in the range between the range of 1/100 until 5%, 7.5%, 10%, 15%, something like that. But in any cases, it becomes much lower than unity, than 100%. So in any cases, for real structure, as I have already said, the motion is damped. Okay, so it's oscillatory and the amplitude is decreasing in time. Okay, so the typical equation of motion for a single degrees of freedom system or for a real building which is represented by a single degrees of freedom system is the one that is rewritten here. Remember that the definition of the fundamental period of the natural frequency and the circular frequency are very important. As we have already underlined, since the fundamental period or the natural frequency or the circular frequency are depending on the ratio between K and M, it is important for us having the possibility of evaluating the stiffness. Okay, but we know if we have a column which is characterized by a certain height and a certain Young's modulus and a certain inertia moment, we can easily evaluate the stiffness. But if we want to evaluate the mass, we have to remember that in practical computation, the mass is given by the value of the weight, for example, in kilonewton, over the acceleration of gravity, g. G is equal to 9.81 meter per square second. Okay? So please remember the equation of motion for a simple building or a single degrees of freedom system. Please remember the different relationship between fundamental period, natural frequency or circular frequency. Please remember that we evaluate the mass as the ratio between the weight and the acceleration of gravity. Now, since we are talking of seismic response, once I have understood how it is possible to evaluate the response of a simple building, which is represented by a single degrees of freedom system, to an earthquake, let's try to evaluate the response. So I know which is the building, basically, and so I know which is the circular frequency and the damping of the building, and I have also measured a certain ground acceleration, U2 dot G. Okay, now it is possible for me integrate the equation of motion of this single degrees of freedom system. Okay, and so, for example, I can evaluate the evolution in time of the deflection, of the acceleration, of the velocity. Okay? But of course, even if at a certain location I have a large collection of earthquake recorded in the past, of course, it is not possible to have such record at each and every location. Okay? So in order to make a seismic analysis, basically I have to do some approximation. First of all, I have to consider that the seismic analysis of structure cannot be carried out simply based on the peak value of the ground acceleration. We have said during the past lecture that the seismic hazard is represented by the peak ground acceleration. But of course, the peak ground acceleration by itself, it's not enough, because we know that different buildings are responding in a different way to the same earthquake, because there is a dependency upon the frequency content of the ground motion and the own dynamic characteristic of the buildings. Own dynamic characteristic of the buildings means natural frequencies and mass and stiffness of the building. So, to overcome this difficulty, the earthquake response spectrum is the most popular tool in the seismic analysis of structure. But what is earthquake response spectrum? Let's see. First of all, we have also to consider another aspect. If we consider, for example, a certain building, and we imagine that the expected service life of this building is 50 years. At that site, we have the possibility of having different earthquakes. Each of these earthquakes will be characterized by a return period, which is, for example, equal to 30 years, 50 years, 475 years. Of course, when I will do the design of a building, what I will obtain is that if we are considering an earthquake with a return period of 50 years, since that earthquake will occur for sure in the lifetime of my building, I need to have no damage under this earthquake. But of course, if I am unlucky and the structure undergoes a very high seismic event, which is characterized, of course, by a much larger peak ground acceleration, what I want from my building is that I will have a lot of damage but no collapse, because a lot of damage but no collapse also mean that there is no loss of life. And for me, having no loss of human life is very important. But now, first of all, we have to understand what is the elastic response spectrum. Okay, so let's try, for example, to have a real time history. For example, the acceleration that was measured in the El Centro, California site in 1940. Probably this is the older seismic records that we have in the literature. Okay, so let us assume, for example, a certain single degrees of freedom system, which is characterized by a certain natural period. For example, let's refer to a natural period of our system, which is equal to 1 second. And so I can have the response in terms of relative displacement, of relative velocity, and absolute acceleration. So, for example, at this time instance, I will obtain a maximum acceleration of more than 5 meters per square second. More or less at the same time instant, I will obtain the maximum displacement, which is equal to about 0.13 meter, so 13 centimeter, for a damping value of 5%. But let's try to do this. Okay, so let's try to apply the same earthquake to different single degrees of freedom system. Okay, so single degrees of freedom system that are characterized by different value of the fundamental period or the natural frequency. For example, first fundamental period 0.5 second, second fundamental period of 1 second, third fundamental period of 2 seconds. And let us maintain, for example, the value of the damping. Okay? Afterwards, we can maintain the value of the fundamental period, but we can increase the value of the damping. For example, 0% damping, 2% damping, 5% damping. So each time I will change the dynamic characteristic of my building, and changing the dynamic characteristic of my buildings also means that I change the mass and the stiffness, so the fundamental period, or the damping, okay, so the dissipation of energy. I will obtain a different response. So different response at every time instance. In fact, for example, you can see that this response is different than this second time history, which is in turn different from the third time history. And if we are going to look, for example, on the right hand side plot, we can observe that on the right hand side also the response is different, and as it has to be expected, when we are going to increase the damping coefficient, the amplitude of the forced response is decreasing. Okay. So when we are talking of elastic response spectrum, what we means is that we are referring to the maximum response of a single degrees of freedom system to a particular input motion. So my idea is, firstly, let us refer to a very special input ground motion, for example, the one that was recorded in 1940 in Helsinki. Okay. Afterwards, first of all, I will consider, and let us, for example, assume that the damping is 5%. Okay. So, first of all, I will refer to a certain single degrees of freedom system, which is characterized by a certain value of the mass and a certain value of the stiffness, which means a certain value of the fundamental period or of the fundamental frequency. I will obtain a certain value, for example, of the displacement. Now I will refer to a second system. The earthquake is the same, the damping is the same, but the fundamental period is different. So different response and different value of the maximum amplitude. And I explore in this way the response of several single degrees of freedom system. Basically, I'm doing something similar like imagining that along the same street, I have several buildings. Each one of these buildings is characterized by the same value of the damping, which is not realistic, but also by a different value of the natural frequency. And this is realistic if every building is different from the others. Because in one case, I have a masonry building of 2 stories. Afterwards, I have a reinforced concrete building of 4 stories. Afterwards, I have a steel building of 20 stories, and so on. All these buildings characterized by different natural frequencies of different fundamental period, but characterized by the same damping, are subjected to the same earthquake. And so I can define an elastic response spectrum in terms of maximum displacement, maximum velocity, maximum acceleration. Of course, every maximum response depends, of course, on the ground acceleration, for sure. But it also depends on the fundamental period of the building and on the damping ratio of the building. So this is the typical computation of one response spectrum or one elastic response spectrum. For example, firstly, I consider a system, a single degrees of freedom system, or a building which is characterized by a fundamental period of 0.5 seconds. I will obtain the maximum response and then I put the maximum response here. Afterwards, I can consider a different fundamental period of the building. For example, 1 second and 1.5 seconds. I will compute the maximum displacement and I will put the maximum displacement here and the maximum displacement here. So by changing the fundamental period of our single degrees of freedom system, by maintaining the same damping and the same earthquake, I will obtain the maximum response of several buildings. Each one of these several buildings is characterized by a different value of the fundamental period of the natural frequency. And so, for example, if I imagine to represent in the same diagram the displacement response spectra for the different value of the damping, for example, I will obtain the red curve for 0% damping, the green curve, this green curve for 5% damping, and for each building, for each value of the fundamental period, I can observe that there is a decrease in the maximum response that is corresponding to an increase in the dissipation of energy, an increase in damping. So it is possible to define similarly some velocity spectrum. For example, if I'm going to look to the damping of 5% and to a building exhibiting a fundamental period of 1 second, the maximum velocity at the top of that building will be here, this number here. Of course, I can obtain also the maximum response in terms of acceleration, the so-called response acceleration spectra. When we are dealing with each one of the elastic response spectra, basically the characteristic of having decreasing response with increasing damping is common, okay? But in the practice, what I will do is not what we can imagine. So obtaining for each single degrees of freedom system the maximum displacement, and after the maximum velocity, and afterward the maximum absolute acceleration. What we will do in the practice that we evaluate the response spectrum in terms of displacement, okay? And afterwards we obtain the so-called pseudo velocity response spectrum and the pseudo acceleration response spectrum. The pseudo velocity response spectrum is simply the displacement response spectrum times the resonant frequency, the circular frequency of our single degrees of freedom system. The pseudo acceleration response spectrum is the spectrum of displacement SD times this time omega n square, so the square of the circular frequency. So in the first case, the ratio, the square root of the ratio k over m. In the second case, in the case of the elastic response spectrum, in terms of pseudo acceleration, we have just to multiply the displacement spectrum by k over m. It is quite obvious to associate a physical meaning to the, so-called pseudo velocity and pseudo acceleration. First of all, let us consider the elastic potential that we have in our elastic system, in our spring, due to the maximum deflection. If we have a maximum displacement SD square, okay, the maximum potential energy is 1/2 times k times the maximum displacement square. if I multiply this energy and divide this energy by m, okay, first of all, I will obtain k over m. But k over m times sd square is omega n square times sd square. So it's equal exactly to the square of pseudo velocity. And so this energy might represent also the kinetic energy, 1 over 2m multiplying the pseudo velocity square. Now let's move to the pseudo acceleration. We have defined the pseudo acceleration as the product of omega n square times the elastic response spectrum in terms of displacement, SD. But omega n square it's equal to k over m. So we will have k over m times SD. But k times SD is the product of the stiffness of the springs times the maximum displacement. Okay, so it is the maximum force which is absorbed by the spring. So basically, k times SD is in mass unit just the maximum force. In fact, omega square SD is equal to k over m SD. K times SD basically is the maximum force. And so if we refer to omega square SD, which is the pseudo acceleration, it is just the maximum force in mass unit. So this value might be used, can be used for design. And so after having understood this, we can easily say that, first of all, when we are dealing with an elastic response spectrum, basically we are dealing with an elastic response spectrum in terms of pseudo acceleration. So omega square times the response spectrum in terms of displacement. So at this point, for example, I know the earthquake motion which is expected in this site. I know, for example, from a simple formula, which is the fundamental period of my building, okay? Because we have seen that the fundamental period is C times H elevated to 3 over 4. I understand also that damping is 5%, okay? The fundamental period is 0.5 seconds. I have that the damping is 5%. Okay, I have that the force is equal to this value of the elastic response spectrum. But of course, I can do this for just one earthquake, or repeating this kind of reasoning for all the possible earthquakes characterized by a certain peak ground acceleration that are expected in the site. So this is the difference between the elastic response spectrum and the elastic design spectrum. So the elastic response spectrum basically refer to a single earthquake. It describes the effects in terms of force of just one earthquake. When we are dealing with an elastic design spectrum. An elastic design spectrum results from the envelope of several elastic response spectra. So I consider the elastic response spectrum corresponding to several input earthquakes, okay? And of course, when I'm doing this, I will obtain an envelope, and the envelope is not so jagged as in the previous case. Sorry. Okay. So you see, the elastic response spectrum in terms of pseudo acceleration exhibit a series of up and down. But if I refer to several earthquakes and I have to make some average between the different earthquakes, basically I will obtain something that there is no more jagged, but it is a typical exhibit a typical shape, increasing from the peak ground acceleration to a certain maximum value. Now this maximum value is kept constant for a certain interval of fundamental periods of structure. Afterwards, there is a first decreasing shape and the second decreasing shape. So the elastic design spectrum is a specification of the seismic design force, of course, as function of the fundamental period and the damping ratio. So, for example, this kind of curve is the one obtained by the standard code corresponding to a damping ratio of 5%. I have to design a building with the fundamental period of 1.5 seconds. For example, 1.5 is in this interval. And so I will consider that the design force will correspond to this value of pseudo acceleration. And so I have just to multiply the value of the pseudo acceleration corresponding to this value of the fundamental frequency of the fundamental period times the mass of the building. So from the elastic response spectrum, once I have evaluated the fundamental period and the damping ratio, I can obtain a value of the pseudo acceleration. Afterwards, I will multiply that value of the pseudo acceleration for the max of the building, and then I obtain the design force. Of course, I can do this for each limit state that I'm going to consider. And of course, we have said that there are the possibility of having different limit state corresponding to different return period of the earthquakes. For example, if the site of my building is characterized by its geographical coordinate, longitude and latitude, okay, I can obtain this value of the longitude on the latitude, and then for a return period of 30 years, 50 years, or 72 years, or whatever we want, we can obtain this value. This is the peak ground acceleration. For example, for 30 years of return period is 0.177 G. For a larger return period, we will obtain, of course, a larger value of the peak ground acceleration. The other coefficients are coefficients that are modulating the shape of the elastic response spectrum. In the Italian code, generally, we refer to the a service time period of a building of 50 years, but to different return periods. Different return periods, each corresponding to a different limit state. Generally, we are dealing with a damage limit state corresponding to a return period of 50 years and to the loss of life return period 475 years, corresponding to the so-called loss of life limit state. So basically, we are considering the damage limit state for which the structure does not exhibit any kind of structural damage. Okay, it behaves in the elastic range. Afterwards, we have to consider the return period corresponding to 475 years. For this return period, we can accept several damage of the structure, severe damage of the structure, but no collapse, so no loss of life. Okay, and generally we design our building for the loss of life limit state if the loss of life limit state is ensured. In the Eurocodes, we also assume that the damage or elastic limit state is fulfilled as well. Of course, what we are doing when we make an elastic design is, okay, I know which is the site of my building, and for example, I decide that I will refer, for example, to the limit state of no damage. Okay, if I refer to the limit state of no damage, and I know the latitude and the longitude of our site, and from this value we can obtain the value of the peak ground acceleration, but also the other value, the value of F0, and then the value of the other coefficients defining the shape of the horizontal component of the design spectrum. Okay, perfect. Generally, I also assume that the damping ratio C theta is equal to 5%. If the damping ratio is larger than 5%, for example, I can obtain this coefficient eta, which is lower than 1, and then I can modify the expression of the elastic design spectrum by using the value of eta resulting from this formula. Okay. In addition, I can also have some coefficient ruling this shape that are depending not also by the geographical coordinate of the site, but also basically by the type of soil. If it is a stiff soil category A, or it is a very soft soil category D. And so we have some shape modification of the elastic design spectrum. If I know, for example, that the soil is a soil A, and I assume, for example, that the fundamental period is equal to 1 second, I will obtain this value of the pseudo acceleration, and then I will multiply this value of the pseudo acceleration times the mass of the building in order to obtain the seismic force. But of course, we have said that this is what we are going to do if we are designed for ideal elasticity. So, for example, we are mentioning a design made for no damage to our building. But we have also mentioned that it is possible to make our design by accepting a non-linear behavior of the structure and large damage of the structure without no collapse. So we have to understood how it is possible to modify the elastic design spectrum in order to account for the non-linear behavior of the building. So when we have that a building behaves in a non-linear way, there are two aspects mainly related to the non-linear behavior of a building. The first aspect is now we are in the non-linear range, so the structure is damaged. But if a structure is damaged, it means that the stiffness of the structure decreases. We know that if the stiffness of the structure decreases, the fundamental period increases. So, what happens to the pseudo acceleration when the fundamental period increases? Generally, if we are dealing with the pseudo acceleration and the elastic period is T1, while in the damaged range we have a lower fundamental period of T2, what happens is that the pseudo acceleration, which means the force, decreases. On the other side, if we are going to look at the displacement response spectrum, of course, when the fundamental period increases, what happens in terms of the displacement is that the displacement increases as well, because much more damage, less stiffness, larger displacement. Okay? So we have to remember that generally an increase in the fundamental period, that means decrease in stiffness, means decrease in the applied force, but also results in change in the and an increase in the response amplitude. Otherwise, a similar result is obtained when we have the damage of a structure, because when we have damage, an aspect which is closely related to damage is that we have dissipation of energy, an increase in dissipation of energy, because now the structure is cracked and we have dissipation of energy between between the two parts, for example, of the crack, because there is some slip and there is some dissipation of energy by friction. So the damping increases. And so if we have higher damping, the higher damping generally generates both a decreases in the applied acceleration and forces and in the displacement response. So the idea in the code is, okay, from the knowledge of the site and from the knowledge of the seismicity in the site, I can obtain an elastic response design spectrum. Elastic design spectrum, which is the force needed to be sustained by the building in the elastic range. Okay, but if I want to design for the inelastic response, what it is possible to do is understand how it is possible to modify the elastic design spectrum in order to obtain the inelastic design spectrum. What is generally done is that we divide the elastic design spectrum by a coefficient which is larger than 1, and this coefficient is denoted in the literature as Q, and Q is named as behavior factor. The value of Q, of the behavior factor, accounts for in an overall way the inelastic response and the ductility. But let us remember that we have inelastic response at several levels, starting from the level of the materials. The steel is the typical material exhibiting a ductile behavior, if instability does not occur. So basically, the steel material is very ductile, but we need also to obtain from the material that it is stable, that behavior is stable in time. But of course, if I have a ductile material, I will also have some ductile cross-section. If I have ductile cross-section, I will also have ductile structural elements in terms of beam and columns. And if an entire structure, a building, a frame is made by ductile structural element, I can also have an overall ductile behavior of an entire structure or of a building. So basically, I can define different types of ductility. In terms of strain, it is generally defined as the ratio between the ultimate strain and the first yielding strain. In terms of ductility, in terms of curvature for the cross-section, and it is defined as the ratio between the ultimate curvature of the cross-section and the curvature corresponding to the first yielding of the cross-section, but also in terms of displacement. In terms of displacement of a structural element, or in terms of displacement of an entire building. If we are referring, for example, to a column or to the overall building, I can say that the displacement ductility is defined as the ratio between the ultimate value of the displacement and the displacement at first yielding. And of course, since I need to have an inelastic response which is stable in time, generally all the international and national code mention that we need to have at least 3 stable cycles of nonlinear behavior. So generally, when we have no ductility, we have basically an elastic response, and the ductility in terms of displacement is equal to 1. So it means that the ultimate displacement is equal to the first yielding displacement. When the ultimate displacement begins to become larger than the first yielding displacement, for example, we can have a moderate displacement ductility in terms of displacement, for example, in the order of 1.5, or very large ductility, for example, in the order larger than 3. But now, the question is how it is possible to transform the elastic design spectrum into inelastic design spectrum. In order to do this, we have to mention 2 important behavior. So the so-called equal displacement principle. The equal displacement principle is applied to structures that are characterized by long fundamental period. So the idea is that when I compare the elastic behavior of my system to the inelastic or elastic plastic behavior of my building, we have that there is an equal displacement of the elastic system and of the elastic plastic system. If the elastic plastic system undergoes the same displacement of the elastic system, of course, I can reduce the elastic force to the inelastic one by dividing for the displacement ductility. So the behavior factor in this case is the ratio between the ultimate displacement and the first yielding displacement. For the short periods, and the short periods is a special range, of course, because we have basically that our structure is very stiff. Short periods means large natural frequencies, but large natural frequencies means very stiff structure. And if I have a structure that is indefinitely stiff, the maximum acceleration is exactly equal to the maximum ground acceleration. And so we have to consider that the reduction in the force due to displacement ductility is less effective than in the case of the equal displacement principle. In the case of short periods, it is said that we are in the range of natural periods that is characterized by the so-called equal energy principle. So in this case, the behavior factor is equal to square root of 2 times mu minus 1. So basically, the idea is that in the elastic plastic behavior and in the elastic behavior, there is the same energy, okay, which is absorbed by our system. But in one case, of course, the system is elastic. In the other case, the system is elastic plastic. So basically, we can reduce the elastic response spectrum by dividing by a coefficient eta, which is equal to 1 over Q. And Q is the behavior factor. For the different value of the behavior factor, ranging for moderate value of the behavior factor, reaching higher value of the behavior factor, we are modifying our elastic response spectrum to our inelastic response spectrum. So the level of the ground acceleration for which we design our system is not the one corresponding to the elastic response spectrum, to the elastic design spectrum, but it is the one corresponding to the inelastic design spectrum, okay? So it's a lower level of acceleration, and so since we have to multiply the acceleration by the mass, it also means a lower level of the mass, okay, and of the applied force. So let's try to make a quite important summary. First of all, the elastic response spectrum describes the effects of just one earthquake on structure that are characterized by different natural period and generally also by different damping. So the elastic response spectrum might be seen as a specification of the maximum force induced by the earthquake on different structure, because we have just to multiply the value of the maximum absolute acceleration by the mass of the building for obtaining the maximum force. So it is a specification of our design force. Of course, since when we consider the design, the real design of a building, we do not design for just one earthquake, but we design for several earthquakes, which are coming, for example, from long distance or from close distance to the site. The elastic design spectrum results from the envelope of several elastic response spectrum, and of course it also depends on the site hazard and on the assumed limit state. Unlike the elastic response spectrum, the elastic design spectrum is not jagged. It exhibits a typical shape. It increases linearly from t equals 0 until a certain value. Now, then we have a constant part, and then there is a decreasing part for the high value of the fundamental period. In addition, of course, also the elastic design spectrum is a specification of the seismic design force. When we are dealing with the design or inelastic response spectrum, the inelastic response spectrum or the design response spectrum is obtained from the elastic one, accounting for the inelastic behavior of the structure, and the inelastic behavior of the structure is accounted for through the behavior factor. Now, since we are around the 12:15, my idea is to have a coffee break for just 1/4, and afterward, for just half an hour, I would like to address this question. So, how I can estimate in real case the seismic forces. Okay, before doing this, okay, let's stop sharing and let's stop resume our lecture. So recording is on, and so I will begin to share again my screen. So the idea is to spend this last half an hour in order to address this question. So basically, how it is possible to estimate the seismic force. And if we want basically to address a question like this, basically we have two aspects to be considered. First of all, the distribution along the height of the building of the seismic force, and afterwards the distribution between each different frame of the building of the seismic force. So what we have to do firstly is this series of subsequent operations. First of all, basically we are assuming that almost all the weight of the building is concentrated at each floor. So, for example, corresponding to the second floor of a building, I can put the weight of the floor, but I will also include the weight of half floor before and half floor after. What does it mean exactly? Basically, I have some walls, okay? So I can assume that half the wall, the floor below, and half the floor after, are concentrated at the level of the current floor. So when we compute the weight of each floor, we have also to consider the corresponding weight of the floor. Afterwards, we have to estimate or to compute, if we are capable of computing this, the fundamental period of the building. Generally, since we know which is the age of the building, and we also know if the building is in reinforced concrete or in steel, and generally we are dealing with the framed structure, it is possible to estimate the fundamental period T1 from the standard codes, from Italian code, from Euro codes, and so on. In addition, since we are dealing with standard code, and we know for each building the site hazard and also the assumed limit state from the standard code, for example, from the Italian standard code, we can estimate the elastic design spectrum. Afterwards, we compute the seismic force for each floor. And afterwards, we have to complete by computing the distribution of the seismic forces at each floor among the different frames of the building. So, first of all, the first thing to do is evaluating the weight of the building, okay? Afterwards, once I have evaluated the weight at the different floor, I can say that the force applied at floor number I are computed by using this formula. Okay, first of all, there is a value FH. Okay, I will explain you afterwards what this value is. Afterwards, for each floor I have to consider the weight of that floor times the distance of the floor from the foundation level, Zi, okay? Afterwards, I have to divide everything for the summation of the product, Wj times Zj. The force Fh, basically, is the summation of the overall weight of the building. The overall weight of the building, W, is of course the summation of the floor weights. So if I have three floors, for example, weight of the first floor is W1, then W2, and W3. The overall weight will be equal to the summation of W1, W2, and W3. Afterwards, SD is the level of acceleration coming from the elastic design spectrum. Afterwards, I have to divide by G, with G being the acceleration of gravity. And there is also a coefficient lambda, but coefficient lambda is equal to 0. Okay? So basically, what I have here in the term FH is the weight, the mass of the building. And the mass of the building is the weight W of the building, or divided by the gravity acceleration times the acceleration coming from the elastic design spectrum, which is dependent on the value of the fundamental period. So afterwards, this value of Fh, which is basically the overall mass of the building times the acceleration of design, should be distributed between the different planes, between the different floors, according to a formula like this. A formula like this has to be expected to give an approximately linear distribution of floor forces. Okay, So something like this. The force which is applied at floor number A is approximately linear, and it depends on this formula. Of course, if I have the distribution of the different horizontal forces at the different level, I can obtain the base shear by summing up all these forces, and I can also obtain the base turning moment by summing up the value of this force times the distance zeta1, zeta2, zeta3, and so on, where zeta at level I is the distance of floor number I from the base of the foundation. And so, for example, we have a typical linear distribution of equivalent static loads. In order to have the evaluation of the linear static force, for example, let us refer to a building like this, in which we have computed the different value of the different forces, different level. For example, W1, W2, and W3 are equal to 1,100 kilonewton. The W at the last level is lower than the other because generally we have a different weight floor of the last floor, but we have also a different height of the lateral walls that are concentrated at the level of the last floor. In addition, the value of the distance between the different floor from the base of the foundation are increasing. So we are increasing from zeta1 equal to 4 meters to zeta4 at last floor, which is equal to 14.50 meters. So at this point, it is very easy to evaluate the seismic force. For example, we can do this by using Excel. So, for example, first column, the level of our floor, I, 1, 2, 3, 4. Second columns, the different weights at the 4 different floor. So the 3 equal weights at floor from 1 to 3, and after the weight at the 4th floor. Afterwards, the third column collects the value of Zi, of the distance between each floor and the base of the foundation. So from 4 until 14.5. Afterwards, here in column number D, we have basically the summation, the value of the product Wi times Zi. And here, marked in yellow, you have the summation of all these elements. So the summation of Wj times Zj. The last coefficient is the so-called distribution coefficient. So for each floor is the ratio between Wi, Zi over this yellow element. We can observe that the summation of this distribution coefficient is equal to 1, because when we are going to sum all the force, we have to obtain the spectral acceleration time the overall mass of the building. And in addition, this distribution coefficient is distributed according to an almost linearly increasing distribution of forces. At this point, once I have obtained the distribution of force along the height, I have to divide different force between the different frame. In order to do this, basically, I have to compute which is the so-called stiffness center of the floor. The stiffness center of the floor, it is very important in order to evaluate this distribution, because generally the force applied at each floor it's applied in the center of mass of the floor, and the center of mass of the floor is corresponding to the geometric center of the floor. But in order to distribute that force among the different resisting elements, I would like to compute the stiffness. If all the column of one floor has the same height, generally I can refer to the value of the inertia moment in a certain direction of each of the resisting element of the floor. For example, here we have a rectangular cross-section which has a width of 30 centimeters and a length of 400 centimeters. So its inertia moment is 1.6 meter elevated to 4. So evaluating the different value of the inertia moment, I can collect all the inertia moments that are corresponding to each alignment of structural elements. For example, I have that the first alignment of structural element includes the element number 1 and the element number 8. The summation of the two inertia, iota 1 plus iota 8, gives an equivalent stiffness K1. Similarly, I have the alignment number 2. The equivalent stiffness K2 consists in the summation of inertia iota 2, iota 6, iota 5, and iota 9. And so, in a similar way, it is also possible to evaluate basically the equivalent stiffness K3 and K4 corresponding to the other two alignments of elements. Okay, perfect. At this point, since I have 4 equivalent stiffness, and for example, I can say that the origin of our system is corresponding to the alignment K1, I can compute the position of the center of stiffness by summing up all this stiffness by their product for the distance. For example, I have K1 whose distance from this point, it's equal to 0. Afterwards, I have K2 and the distance is 5. Then I have K3 and the distance is 5 plus 4 equal 9. And afterwards, I have the spring K4 and the distance of the spring K4 from the origin is 14. By computing the coordinate, the x coordinate of the center of stiffness, I can obtain that the position of the center of stiffness is about 0.18 meter far from this point. So it is very close to the origin or to the spring K1. Why it is very close? It is very close to that element because we have the cross-section number 1 exhibiting a dominating inertia with respect to the others. And so the center of stiffness is generally much closer to the stiff part of the structure. At this point, I have an eccentricity which is equal to the difference between 7, and 7 is the position of the center of mass, minus the eccentricity, the position of the center of stiffness. So we have 6.82 meters. At this point, we can distribute the different action between the different elements, basically saying that we have the action of an applied force P. If the applied force P is applied in the center of the stiffness, there is a uniform distribution of that force between the different springs or between the different alignment. But we have seen that that force is not applied in the center of stiffness. It is applied in the center of mass. So the eccentricity, the distance between the center of stiffness and the center of mass is about 7 meters, 6.82 meters. So there is a bending moment which is equal to the product of the force times the eccentricity that we have to distribute between the different elements according to their distance. This formula is basically very similar to the one that we have commented and discussed in bolted connection and related to what we have denoted as case 2. Okay, so by doing this, it is possible to have the distribution of the action P between the different parts of the structures. Okay, and so it is possible to divide the force for each floor between the different resisting frame of, if we want, between the different vertical columns. Basically, this is another example. Of course, I will send you those examples in order that you can very easily, but also quite easily, well, quite in a quiet way, you can repeat the computation we are very quickly describing in this case. You can observe that now the distribution between our elements is more or less symmetric. So we have basically to expect that the same part of the floor action is supported by the stiffness by the alignment consisting of column number 1 and column number 7, and the alignment consisting of column number 4 and column number 7. And similarly, also this distribution of the forces between the central frame is basically the same. Of course, the distance between the center of mass and the center of stiffness, in this case, it's equal to 0. And so we can basically distribute the different forces by in proportion, in direct proportion to the stiffness of the spring K1, K2, K3, and K4. Okay? And so if this is the distribution of the different forces along the 8, which is quite different from the previous one I have explained, you have basically the distribution at the different floor of a structure of every one of the different forces. So at each floor, you have different forces, F1, F2, F3, and F4. Okay, but at each floor, the force F1 is distributed between the different elements. And so, for example, the first spring, the first alignment, assume a force that is equal to 29.2 and so on. This is, of course, the case in which we have a non-symmetric plane. In the case we have a symmetric plane, of course, T1 and T4 basically are the same number at basically the different floor. Okay, so we are exactly at 1 o'clock, and as we wanted, as we basically scheduled, we have basically completed the lecture of today. So now I'll stop